All right, we're going to be continuing from where we left off yesterday. So we were looking at polar coordinates as kind of a system to refer to various points. Yes, we can refer to things in terms of some kind of shift in the x direction, some kind of shift in the y direction, but we saw that there might be some utility, or at the very least I've claimed that there might be some utility in instead kind of conceptualizing as these points in terms of some kind of rotation along some kind of radius for a circle. We're going to be taking this framework and we're going to be applying it to a couple of different things. First and foremost, we're going to be taking a look at how we can integrate what we have done with our polar coordinates and see how this meshes with imaginary numbers. Or maybe not imaginary, but complex numbers. This might feel like a little bit of a strange jump of like, okay, well, before we were talking about these like two-dimensional points, and now we're jumping to just like this complete number system. Why would there be this kind of translation here? And really, this is because for all intents and purposes, complex numbers act a whole lot like two-dimensional points. For instance, let's say we had the complex number, we'll say z is equal to 2 plus 3i. The way we would visualize what this is trying to communicate is we would think about some kind of real axis, which is generally speaking denoted as if it is the x-axis, and some kind of imaginary axis, generally speaking denoted as if it is the y-axis. And so to graph the number 2 plus 3i, we would travel 2 in the real direction, we would travel up 3 in the imaginary direction, it would end up being right here. Now, to be very, very clear, this isn't the point 2 comma 3. Right, this is an imaginary number, or complex number rather. It's not a point, it's not two real values. But what we can very easily construct, very, very easily construct, is a correspondence between the imaginary complex numbers and our two-dimensional points. Very, very simply, if we have a plus bi as a complex number, then it does us pretty well to think of this like the point a comma b. So technically not a point, effectively a point though. All right. We'll see this is going to actually show up a little bit when we are actually converting what we have with the complex numbers into their polar form. What we'll end up with is, again, not a point. So you aren't going to have like r comma theta like before, but we'll have something that's basically r comma theta, just adjusted ever so slightly. Now, again, with that goal in mind, trying to think about our r comma theta as a representation here for our imaginary values here, our complex values here, where this is our theta, this would be our r. It makes a lot of sense that we are going to want to kind of flesh out what r is going to look like. Good news for us is if we felt really, really good about what was going on in 6.1, it's pretty much the exact same thing. The only difference here is the terminology that we might be using. So before we just talked about this value of r like it is the radius, we're going to be a little bit more explicit with kind of our definitions here. generally speaking, when we are talking about R in terms of our complex numbers, you will either hear me refer to this, you'll hear me generally refer to this as the magnitude of the number. But from a perspective of like what you'll see on Pearson, you'll also sometimes see this referred to as the absolute value of our complex number. So absolute value and magnitude kind of conveying this same idea where we are saying we don't care about direction. Think of theta as representing something about the direction that we are pointing. We care only about how far away we are from our center. You could also think of the magnitude or absolute values like being a measure of the distance from 0. It's not a bad way to think about it. I guess technically 0 plus 0i is maybe the best way to write this. And we could do our distance formula here. Sure, that's fine. But ultimately, this is going to amount to pretty much exactly what we were seeing before, where if we have a triangle like this and we are looking for our value of r, then r is, generally speaking, just going to be the square root of a squared plus b squared. All right, it's the distance formula. It's the Pythagorean theorem. It's everything that we have done with our radius up until this point. And now I'm just saying, okay, well, we have a new word to refer to it with. I might call it the magnitude, or I might call it the absolute value. I'm probably going to call it the magnitude, which will have ties into what we do a little bit later. All right, questions here. Actually, one thing before we talk about questions, I want to note something very, very specific about our magnitude formula. Our complex number is in the form a plus bi. Our magnitude is the square root of a squared plus b squared. What is very, very much missing from our magnitude formula that we see in our kind of arrangement for our complex number? Yeah, we don't see I. That's really, really important, actually. The value of b is not, for instance, if we're looking at this imaginary number here, b is equal to 3. It is not equal to 3i. Think of the I as just telling you that you're going up rather than sideways. All right, so the I is conveying some kind of direction information. And the number in front of it tells you how far in that particular direction that you're going. Essentially, the I tells us that it's acting like the y coordinate, and not having an I tells us that it's acting like the x coordinate. It's not changing the value. It's not changing the size. Don't include the I in your metric there. It's really, really important because when we square I, we get a negative value. And so doing a squared minus some number is obviously going to give us a very, very different magnitude than a squared plus some number. We want to make sure that we are using just the coefficients, and the I is just there to tell us that we are acting like the y coordinate instead of acting like the x coordinate. Not that we are the y coordinate, just that we are similar to, that we are pretending to be the y coordinate. All right, questions with our magnitude definitions here? All right. Take a stab at example 1. So trying to find the magnitude of those 3 complex values given. We'll take, let's say, we'll take 5 to 10 minutes on this. So example 1, A, B, and C, trying to find the magnitude or, I didn't say magnitude, on Pearson that would say absolute value, trying to find that value of R for what was so think of this as being the x and then the plus I component as being the y. So you're not, so z is like our, just like the variable that we use to solve complex numbers or trying to solve for, or not solve for, you're basically just like to the first use.
You might use this.
Yeah, basically. And then what would the value of b be? Yeah, exactly.
Oh.
Yeah. 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 Okay, so what's our value of A for A? Okay, and then what would the value of B be? So how much in the I direction or is that telling us? Okay, thank you. Yeah. It might be helpful to actually rewrite it in the form of A plus BI, like what would the value of B be for that to be equivalent to them, and then that makes it just a lot more clear. Yep, that's good. This one, when we square the -3 for the value of b, it's going to become +9. So I would double check what the you're going to end up with a number that you can't actually take the square root of, but just making sure that the a squared b squared is positive. Still looks good. These interviews look good. Let's just plug them into that distance formula basically. Pythagorean here. What is your value of A? What is your value of what is our value of A or X? You can do X as well, but what is our value of X? What is our value of Y? So okay, and so what is the Y component here? We don't see anything, but how many I's do we have? 0, so that would be your value of Y. Is I a part of these?
So we just, okay. So if there's an I, do I have to put it in this?
Does this have any I's in it? No. Yeah, the I is we'll learn a little bit more about this in the next week or so. Think of the I as a direction vector. It's just telling you that you go up instead of going down with that particular component. Yeah, that works. Yep, yep. Yes. And we're getting to what that's gonna look like, but it's very much in the right direction. All right, overall looks pretty good. One thing that my first period did a really good job of that I wanted to highlight as just like something that they found very, very helpful was when we're looking at an example like A and B, where it doesn't look exactly like our other complex numbers, it might be helpful to rewrite everything in terms of this A plus BI. So for instance, 2, we could think of as like 2 plus 0i, and 3i we could think of as like 0 plus 3i, just to make it really, really quite clear what A is, what B is. So in the case of A, what are our values for A and B? 2 and 0. And so our value of R is going to be the square root of 2 squared plus 0 squared. I get that this is 2, which should hopefully be comforting. We would hope that the absolute value of 2 is 2. And that is, in fact, exactly what we find. All right, what are our values for A and B for B? Zero and 3. So again, R is equal to the square root of 0 squared plus, notably, just 3 squared, which is going to give us a value of 3. We would expect that if we were to have just a point on the imaginary axis just down here, how far would we be? Well, that should just be 3 down. All right, one more. What are our values for A and B for C? 5 and, just to be precise, I would say probably -3. It doesn't matter in terms of the magnitude, but it is something that we will need to factor in later for our direction. Importantly, PEMDAS, very, very important here. This is 5 squared, which since it's positive, we don't really need the parentheses. But 5 squared plus, in parentheses, -3 squared. We want to make sure that we are squaring -3, not squaring 3 and then making it negative, for which I get that this should be the square root of 34, which we will just leave as that. Questions with example 1, finding the value of R, finding this magnitude here. Hopefully pretty much exactly like what we were doing with our polar coordinates to find that value of R, taking the square root of x squared plus y squared. In this case, a squared plus b squared, which is effectively the same thing. All right, so that's half of our goal. If our goal is to kind of fit our imaginary numbers into this polar coordinate framework. We now have the ability to figure out r. The only thing then that we are missing is how do we find out what theta is? But we've worked that before. For instance, we know a couple of things. First and foremost, we know that. Well, actually, there are a couple of things that I want to. No. We'll do this first. So very similarly to like what we were doing before, where cosine of theta was x over r. We'll see that cosine of theta is a over r, and sine of theta b over r. And figuring out what theta would need to be here. Using these equations and maybe some unit circle information or maybe some inverse trig in order to figure that out. But I think importantly is going to be the form in which we get this, because we're not aiming for a point, right? We're not aiming for r comma theta. But if we think of A as being like the x coordinate and B as being like the y coordinate, then a very quick substitution should tell us that A is equal to r cosine of theta, and that B is equal to r sine of theta. And so our complex number Z should be able to be written in the form of r cosine of theta plus I r sine of theta. Factoring out an r, we might write this as r times cosine of theta plus I sine of theta. And it turns out that this is used so commonly in terms of our complex numbers, in terms of writing our polar coordinates. Mathematicians were very lazy. This is a lot of information to kind of write out. You will see this abbreviated. I will abbreviate this, and you can abbreviate this as CIS of theta, which literally just means cosine plus I sine of theta. So when I say basically all of our kind of complex numbers here, rather than writing them in the form of r comma theta as like a point, you will instead see them written as r CIS of theta. But really, this is like our r comma theta. It's basically the same thing. It's just the CIS tells us that, in fact, what we are looking at is a complex number, not a point. But we're going to solve it like it's a point, right? We're not really changing anything that we're doing. It's going to be very much the exact same thing that we've done up until this point. So let's take a look at 2b here. 2b is a little bit tricky. A and C, which I'll give you guys time here in a second to work at yourselves. Not too horrible. Stuff that we can generally do with our unit circle knowledge. We're going to find that B is a little bit trickier than that, though, unfortunately. So we're looking at B. We are given that our Z is equal to 4 minus 3I. We'll see why I want to do this momentarily. What quadrant does this complex number live in? Yeah, this is going to be a quadrant 4 complex number. All right. And we can go ahead and start trying to figure out, okay, what is our value of R? What is our value of theta? I get that r should be the square root of 4 squared plus negative 3 squared, which is the square root of 25, which is, of course, going to be 5. So now we need to figure out theta. We're going to do this in the exact same way that we did before, where we are going to write out the equations. This is either that cosine of theta is equal to a over r, or that actually should be and that sine of theta should be equal to b over r. All right, unit circle knowledge time. Do we know the theta that gives us an x value of 4/5 and a y value of 3/5? No, that's not unit circle knowledge that we have. Okay, so that's a little bit of a problem. The only other way that we can approach this, the only other way that we can find this theta is by using our inverse trig. So let's construct two different inverse trig statements here. One of which will work, the other one will fail. But we're gonna build both of them. For instance, if cosine of theta is equal to 4/5, the way that we might rewrite this in terms of our inverse trig statements would be that theta should be equal to, and you could either do arc cosine or the cosine to the -1, cosine inverse of 4/5. And if sine of theta is equal to -3/5, then theta should be sine inverse of -3/5. So both of these are, I'm not tricking you, both of these are valid ways to rewrite the statement here. Only one of them is giving us the theta that we actually want. Which of these two statements is the theta that we're looking for? The cosine inverse? Are you saying the cosine inverse? Why? But why do we want the x value instead of the y value? There's something more specific about our inverse trig functions and where we are looking right now that will clue us into which of these thetas is the correct one. We're in the fourth quadrant, and so which of these two statements, cosine inverse of 4/5 or sine inverse of -3/5, represents a fourth quadrant angle? Other one. Sine inverse spits us out where? Which two locations? What is the range of sine inverse? It's not going away. All the way back from that unit 4 test. Still here. Still, I guess actually that was the unit 4 test. Still here. Where does sine inverse spit us out? What two quadrants? 1 and 4. Cosine inverse spits us out in 1 and 2. And so my first statement here is a quadrant 1 angle. And my second statement here is a quadrant 4 angle. Yeah.
How do you know which quadrant?
That's a definition. That was what we did way back at the end of Unit 4, where we were looking at our inverse trig functions and determining where sine would spit us out, where cosine would spit us out, where tangent would spit us out. And did we have a way to reach quadrant 3? No, we would need to figure out some clever, cheaty ways to get into quadrant 3. They're there, they exist, but they are, I would say, slightly beyond what we're looking at here. And not too far beyond. It would be a good like bonus question. All right, so our theta is actually very decidedly not the first statement, the cosine inverse statement, but instead is this sine inverse of -3/5, and we are okay with leaving it like that. All right, in fact, that's the most precise way that we can write this. We have our r, we have our theta, our value of z here is going to be equal to r CIS of theta, which is 5 CIS of sine inverse of -3/5. Yeah, Dylan. Sine inverse of -3/5, right? Where this is just our r, and this is our theta. A and C should be a little bit more approachable. Those ones are actually just unit circle information. So you should be able to tackle A and C without needing to invoke our inverse trig statements. And so I will say, let's take a minute. We'll say 10 minutes. Take a stab at A and C. And just as a piece of advice, it might be a little bit easier for you if you simplify a little bit that value of r that you get for A. Just so that you can kind of see what the unit circle information is going to look like.
What's the form? Yeah, so this would be like if it were a coordinate, but what is the like final answer? Yeah, it's gonna be exactly like that. Yep, yep. Yeah, exactly. You could do like 3 in parentheses cosine of theta plus I sine of theta, but like that's the compression of that. Oh, it's good for a value of R. And so it might be easier to think of this as like 18 is like 3 times 3 times 2, so thinking what breaks out of the square root of what stays behind, and then doing the like x over r for cosine, y over r for sine, figuring out what that theta is going to be. And it should be the unit circle, so that one should be a little bit nicer. Negative. So you already incorporated the fact that it's negative into arriving at this answer. So the values that you get here are the values that you get. Like you're happy with 6, you're happy with this, that. And generally the way that we're being geared to do this will always have positive R, positive theta. It's just what we're going to end up with. Is this the correct form? Are we looking for a point? Yeah, so how would we rewrite it? You're like basically there. This would be like 9 out of 10. But you just need to reformat it to this, where this would be like 3 root 2 CIX. Yeah. Looks good. What's our R? Yeah, which you are. Yeah. So 1 over root 2 is actually unit circle information. We generally don't see it like that though. So maybe try rationalizing the denominator to see like what that value actually is. How do we know what quadrant it's going to be? Yep. Yep. So that'd be quadrant. Yep, exactly. Yes, we actually can evaluate this. This is actually a unit circle. Yeah. So 1 over root 2, generally not how we see that number. Try rationalizing the denominator to see what it is. But this would be like 9 out of 10. But try like multiplying by like root 2 over root 2 to see sort of what it becomes. Root 2 over 2 is the equivalent of that.
So my answer is formatted like this one.
Yeah, so essentially we're just able to evaluate what sign inverse of that
like
is. It'll
root 2.
Well, it'll have there's a what's the value of theta that would give us a y value for 2.
So positive 1.
Yeah, so we're in quadrant 1 here. Yeah, 5 over 4. So just instead of this sign inverse statement, you would just write 5 over 4. Yeah. It's not that what you have was wrong. It's just that we can evaluate it. Yeah, we can just simplify it a little bit more. Which is why like it would be like a 9 out of 10. I don't know if that's like it would probably get a -1, but like it's there you go. So what is our value of theta? That makes, now this is -6 over 6, right? -6. Our value of b. B over r would be -6 over 6. So we're trying to find what is the value of theta that would give us a y value of -1 on the unit circle.
All right, let's take a look here at what we've got. So for A, this was 3 plus 3i as our complex number. What is our value for r that we found? Square root of 18. And then how did we simplify this? This was 3 root 2. Very good. And so the two equations that we get, cosine of theta equaling a over r, so this would be 3 over 3 root 2, and sine of theta equaling b over r. Now 1 over root 2 is different than what we're used to kind of seeing here, but this is equivalent to something that we actually do know. What is this the same as? If we rationalize the denominator here, what do we end up with? Root 2 over 2 for both. And so what is the angle that's going to give us positive root 2 over 2 for both x and y? That's going to be pi over 4, noticing that we are in quadrant 1 here. So we are looking for the quadrant 1 angle that will give us that. And so our final answer here, we have our value of r, we have our value of theta. We know that z should be equal to r. You could either do 3 root 2 or the square root of 18, that's fine. CIS of theta. If you wrote this, you'd get most of the points, but we are looking for a complex number, not a point. And so the best way to write this, not the best, it's the correct way to write this would be what we see here. Yeah, tell me. If you do the prime factorization of 18, you should get 3 times 3 times 2. Low security prison, so you only need one buddy to escape prison. Your buddy dies in the process, so the 3 gets to break out, 2 gets left behind, one of the 3 dies. 3 root 2. We already did B. For C, this was negative 6i, which may be a better way to think about this is like 0 minus 6i. So where A is 0, where B is negative 6. For R, I just get 6. 0 squared plus negative 6 squared, take the square root, should get 6. So my two theta equations, I get that cosine of theta is 0 over 6, and that sine of theta is negative 6 over 6. So we're looking for the place, the value of theta, where cosine, where the x value is 0, and the y value is negative 1. What is that value of theta? Three pi over 2. And so we end up with z equal to 6 CIS 3 pi over 2. Questions here with our converting from rectangular imaginary numbers or complex numbers to polar complex numbers. Hopefully it's like exactly the same as what we were doing with the points, just now in a slightly different form. So hopefully if we felt good about 6-1, we're feeling pretty good about this. All right. We're gonna look at the utility. We're gonna look at like a quick little proof here, and then we'll come back. We'll work a couple examples. Not too many. We'll be done here momentarily. But right before we get out for lunch here, I want to take a look at why on earth would we? What's our motivation here? Why would we want to work these problems in the polar form? Why would we want to put complex numbers in their polar form rather than their imaginary form? If we think back to 2.1, when we were first working with complex numbers, when we were first doing operations with complex numbers, adding and subtracting rectangular complex numbers was pretty easy, right? You add the A's, you add the B's, that's not too bad. You subtract the A's, you subtract the B's, that's not horrible. Multiplying them kind of sucked. It wasn't like horrible, but you needed to do the Punnett square, and then you ended up with like I squared, and so you needed to kind of do that whole process. So that was not great, but it wasn't terrible. Dividing them was pretty awful. Where you had to do like two Punnets, where you had to like use the complex conjugate and try and do out the Punnett square on the top and the bottom, and it split everything apart. That ended up being pretty rough. The good news for us, and why we see a ton of utility in actually writing complex numbers in their polar form, is that those two more difficult operations become super easy. So let's consider this. Let's say we have two complex numbers. We'll call them Z1, which will be equal to R, R1 times cosine of theta, plus R1 sine of theta. This is a complex number just written out in its polar form. You would condense this into CIS of theta, but for the purpose of my demonstration, we're going to leave it like this. And we have a second complex number, Z2, which is R2 cosine, this should be theta 1s as well, not necessarily the same theta, cosine of theta 2 plus I R2 sine of theta 2. And I want to multiply them together. And we're going to say that dividing is going to basically give us the same result because it ultimately does. But let's say we want to do out this multiplication. So Z1 times Z2. Well, this would normally be a pretty messy Punnett square. You can check this yourself. But if you FOIL out what we get here, we should get R1 times I R2 cosine of theta 1 times sine of theta 2. Okay, so that's like first times, that's the outers being multiplied. Actually, maybe, sorry, we're going to do this in a little bit of a cleaner way. If we do, so foiling, so first times first, I get R1 times R2 times cosine of theta 1 times cosine of theta 2. This is first. We are going to add that with our outer. Actually, probably best is adding it with the last. So this would be I squared R1 times R2 sine of theta 1 times sine of theta 2. This is our last, plus R1 R2 times I cosine of theta 1 times sine of theta 2. This is our outer. And then another I, R1, R2, cosine of theta 2, sine of theta 1. Like, what do you mean? I thought you said this was going to be easy. I thought you said this is going to be nice. And it actually ends up being fairly nice. What is I squared? Just 1? -1. So this is really like subtracting this second term here. We only see this 1I squared. This is like subtracting what we have here. And so if we look a little bit deliberately here at what I have boxed, R1, R2, cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2. Cosine of an angle times cosine of a different angle minus sine of an angle, sine of that different angle. That's our cosine difference formula, or cosine sum formula. This is the same. We're almost done. Actually, yeah, we'll pause here. We'll head to lunch. We're like 1 line away from being done. But this is going to collapse very nicely. We're going to end up with a really nice product for our trig functions here. But we will resume this after lunch. I will see you all at 12:25. All right, we'll got like one more kind of observation to make. Or we can consolidate this. Where have we seen this before? Where we have like cosine of an angle, like cosine of A, cosine of B, minus sine of A, sine of B. Where have we seen that before? Yeah, it's like our sum and difference. Now, is this behaving nice or mean? This is mean, right? Notice how all of our cosines are grouped together. All of our sines are grouped together. Notice how we've got this minus. And so since it's mean, we would expect this piece here to be equivalent to R1, R2 times cosine of A plus B, or theta 1 plus theta 2. Give myself some more space. This is R1, R2, cosine of theta 1 plus theta 2. And down at my bottom here, well, both of them have i's, so we are actually able to add them. They are like terms. We also have this R1, R2 thing here, and we've got cosine of some angle times sine of a different angle, so like cosine of A times sine of B plus sine of A, cosine of B. What does this look a whole lot like? Nice or mean? Nice. Notice the sines and cosines all getting along here. This is going to be sine of theta 1 plus theta 2. And so while this looks like some kind of giant massive mess, in reality, this condenses very, very nicely. If I have Z1 times Z2, if I have two polar complex numbers being multiplied together, the way we evaluate this is actually really, really easy. All you do is multiply the magnitudes and add the thetas. This would just be, in this case, R1, R2, cosine of theta 1 plus theta 2, plus I R1, R2, sine of theta 1 plus theta 2. And then again, we see here this construction. We've got some kind of magnitude. In this case, the product of our original two. And we've got cosine plus I sine. This is the exact same as R1 times R2, CIS of theta 1 plus theta 2. So what before was an incredibly difficult, trying task is now substantially easier. And we're not going to go over the proof of this, but the good news for us is that division, which again was also incredibly difficult, has a very similar kind of product here. So for our, I'm about to rewrite this. So for our product, where when we have Z1 equal to R1 CIS of theta 1, Z2 equal to R2 CIS of theta 2, how our product is the product of the R's, CIS the sum of the thetas. For our quotient for division, we get something incredibly similar. We have the exact same setup. So we'll assume exact same thing here, where if I want to do Z1 divided by Z2, which before, remember, was that awful, incredibly hard kind of, maybe not incredibly hard, but fairly difficult task. Now, this is just a matter of dividing the magnitudes. And if before, when we're doing multiplication, we add the thetas, what do we think we do when we do division? Yeah, probably subtract the thetas. So again, these operations that before were quite difficult are in this polar form trivially easy. Maybe not trivially easy, but like close to trivially easy. Very, quite straightforward in comparison. Question, yeah, Dylan. This is the last line. Yeah, that is the last line. All right, let's take a look at this in action here. So looking at example 3, We are asked to find the product z1 times z2, as well as the quotient z1 divided by z2 for the complex numbers as they are given. We'll do the product together, and then I'll give you guys a little bit of time to work on the quotient here. We know that z1 times z2 is the same as multiplying those values of r and adding those values of theta. What are our r values for our two complex numbers here? 12 and 3. So 3, or we'll do this in order. So this is 12 times 3, CIS. And what are our values of theta? Yeah, pi over 18 and 4 pi over 9. Uh, 4 pi over 9, that's the same as 8 pi over 18 plus pi over 18. This is going to be 36 CIS of 9 pi over 18 or pi over 2. Which we could convert to rectangular form. That wouldn't be too hard. Pi over 2, the cosine component would be 0. The sine component would be positive 1. So this is equivalent to 36i. But since we're not asked to do that, we can also just be more than happy to leave it in our polar form here. So we'll say take like, I guess we'll give it another 5 minutes. Take it another 5 minutes. Try the division. Try the quotient. Exact same numbers, exact same everything, but we're just doing this process with the division instead. I think that would be negative, because it would be in the, okay, but otherwise it's perfect. Yep. Good. Nice. That's great. That's good. So when we do this division, we subtract. Look at this. So we divide the r's, subtract the things. Yep. Yep. Looks great. All right. So for our division, so for Z1 divided by Z2, this is simply R1 over R2 times the CIS of theta 1 minus theta 2. In this particular case, 12 over 3 CIS of pi over 18 minus 4 pi over 9. We should get that this is 4 CIS of negative 7 pi over 18. Questions with our multiplication and division of complex numbers now in polar form? All right. We're going to stop there for today. We'll look at some applications of this next. So what are we actually going to be using this kind of multiplication division for a nice consequence of it? We've got about a little over 5 minutes left. We do have the, again, 6162 classwork that Pearson to be working on. So I would recommend taking this time to work through that.